Good morning and welcome to Tech 293 on Tuesday, March 16th. I hope you enjoyed Lab 6 last week in the lab. I always think that's a pretty enjoyable and fun lab. I enjoy doing it. Speaking of fun labs, we got some fun labs coming up after the next exam. I always really enjoy Labs 7 and Lab 8. Those are some of my favorite labs as well. Lab 7 in a couple of weeks is going to be about two parts. First, there's heat treatment. And then we're going to use those heat-treated specimens, different kinds of heat treatment applied to different specimens, and we're going to break them, and we're going to see how much energy it takes to break different kinds of heat-treated specimens. So that's always fun, partly because it's fun to use the Sharpie V-notch testing machine, but also partly because we get to use liquid nitrogen. So on that day in class, I usually go over to the science lab building and I pick up a bucket of liquid nitrogen and I bring it back, and we'll use that opportunity to play around a little bit with liquid nitrogen, which is always fun. And that's Lab 7. And then Lab 8, you can look on your schedule and see when that is, but Lab 8 is a week or two after Lab 7. And with that one, we're going to be talking about beam bending, like how much force it takes to bend a beam, like an I-beam or a bridge or something like that. And so in Lab 8, in your lab groups, you're going to design and build your own beam. It has to be made out of wood, and I'll give you some parameters that you have to abide by to make it fair. But you have to basically design and build your own beam, and then we will test it in the lab, in Lab 8. And there'll be a little bit of extra credit for who can build the strongest beam and who can best predict the load that their beam can support. And it'll be a fun little competition. So those are some labs that are coming up in the class. Those are probably some of my favorite labs in the class. I really enjoy, almost all of them, but Labs 7 and 8 are probably two of my favorites in the whole class. But before we get to that, we do have an exam coming up. I'm looking at my schedule right now, and you can see that on March 18th, we have Exam 2. As you can see on the syllabus, Exam 2 is going to cover tensile testing and compression testing and ferrous metals and non-ferrous metals. Those are the main things that Exam 2 will be on, but there's also some of the basic stuff from the first third, not all of it, but that basic materials science, overview of materials testing, that kind of stuff, the really basic stuff is important. So that stuff is still potentially going to be on Exam 2 as well. There won't be anything from hardness testing on Exam 2, but that basic materials science stuff like lattice structures and types of bonding and stuff, that's important to tensile testing and compression testing. The reason it's important is because that kind of basic materials science determines how the materials are going to behave when you put them into a tensile test or a compression test or really any other type of materials testing. So the purpose of this video is to do a bit of review for Exam 2. I think I'm going to start out by doing some review calculations because I think that's always something that students want more practice with. So I'm going to do some more review problems. But I will remind you, before we do that, I already made a video with review calculations as well. So I would strongly encourage you to do that, whether you have or haven't. Either if you've watched it already or not, I would encourage you to go back and watch it again on page 37 and 38 of the lab manual. And try to do that worksheet on page 37 and 38. Try to do that without watching the video, and then go back and after you do the calculations, then watch the video. And that way, if you got stuck, you can figure out where it is that you went wrong or something like that. So if you haven't watched that video, then you definitely should watch that video. Even if you have watched that video, I think it'd be a really good idea to do it again, because these are the type of questions that you're likely to see on the next exam, on Exam 2. So that would be a very good practice. Also, the practice problem that I will show you in just a minute, I'd encourage you to solve that by yourself as well, and then come back and follow along in the video. So I'm going to go ahead and switch over to my document camera to do a couple of review problems. All right, here's the first problem that we will solve today. We have a specimen made from material X, and it has these mechanical properties. It has a yield stress of 50,000 psi, an ultimate tensile strength of 60,000 psi, and an elastic modulus of 500,000 psi. And we have a specimen of material X. It is a cylinder with a diameter of 1 inch and a gauge length of 4 inches. And then we apply a load or force of 40,000 pounds force. How much will it stretch, which is the change in length, delta L. What is the delta L here? All right, so we start thinking about how we can calculate delta L. We know we can calculate delta L if we know the original length, which we do, and the strain, but we don't know the strain. So we can't use that directly. But maybe we can find the strain. We can find the strain using the equation for elastic modulus. We can find the strain if we know the elastic modulus and the stress, right? Because E equals the stress divided by the strain. But we don't know the stress. All right. But we can find the stress if we know the load force that's applied and the cross-sectional area. We don't know the cross-sectional area directly, but we can find it because we know the diameter is 1 inch. All right, so that's the process we're going to use. We're going to use the load force and the cross-sectional area, which we'll find in a second, to find the stress. Then once we know the stress, we'll use that and the elastic modulus to find the strain. And finally, once we know the strain, we will use the strain as well as the original length to find the change in length. All right, so it's kind of a three-step problem. All right, so like I said, the first step is to calculate the stress, but we're going to find that there's a step we have to do even before that. We know that the stress is equal to force divided by area, and the force is 40,000 pounds force, but what's the area? So we have to do that actually even before what I would call step one. So the area is equal to pi r squared. That's the cross-sectional area because it says it's a cylinder. All right, so be careful. It won't always be a cylinder. I could tell you it's a square or even a rectangular cross-section, but this is a cylinder. Its cross-sectional area is a circle, and the area of a circle is pi r squared. So the area is pi times the radius squared. And the radius, if the diameter is 1 inch, then the radius is 0.5 inches, and we square it. Remember your order of operations, you need to do the exponent before you multiply it times pi. So take 0.5 squared, and then take it times pi. And we get a cross-sectional area of 0.7854. All right, I'm probably going to keep a few more significant figures as I'm doing the calculation, and then I'll round it off at the end. All right, and I recommend you do the same. Keep a few more significant figures. Keep at least 4 significant figures during the problem, and then after you're done with the problem, for your final answer, you can round it off to usually 3 significant figures would be fine. So let's call this, for right now, let's call it 0.78540. 0.78540. And the units are inches squared because we took inches and we squared it. So your units are inches squared. All right, now we can take that cross-sectional area and bring it down here. 0.78540 inches squared. So now I can do this calculation, 40,000 pounds force divided by 0.78540 inches squared. 40,000 divided by 0.78540 gives me 50,929 psi. 50,929 psi. All right, so now we should pause. If you remember, this is really important. Whenever you're doing a calculation like this and you solve for the stress, it's really important after you solve for the stress, you have to pause and compare to the yield stress. right? Because we can't go any farther if it's above the yield stress. Why can't we go any farther? Because the elastic modulus doesn't apply above the yield stress. So it's not even like we just shouldn't do this calculation above the yield stress. It's literally that we can't. There is no simple relationship between stress and strain above the yield stress because E, the elastic modulus, doesn't apply above the yield stress. So you can see here, 50,929 psi is definitely it's slightly, but it's above. It's slightly above the yield stress of 50,000 psi. So it's above. The stress in this problem is greater than the yield stress. So we have to stop. And we can't solve the problem because the stress is greater than the yield stress. And more specifically, like I was saying just a minute ago, there is no simple relationship between stress and strain above the yield stress. We can't just use this fact that the elastic modulus is this number above the yield stress because this doesn't apply above the yield stress. All right, so that's actually it for this part. If I asked you this exact question on an exam or quiz, then you wouldn't be able to do it. You'd have to stop and you'd have to compare the stress, and you'd have to say that you can't do it because the stress in the problem is greater than the yield stress. All right, so we can't apply 40,000 pounds force because that's going to exceed the yield stress and we're going to get permanent deformation or plastic deformation. But let's say we modify it and say, now suppose the force, instead of being 40,000 pounds force, let's say, okay, it's only going to be 30,000 pounds force. All right, now how much? Now how much will it stretch? All right, so we can start the problem just like we started up here, except we already know the cross-sectional area, so I won't redo that. It's the same specimen, same dimensions, so this is still the same cross-sectional area. But now let's go ahead and calculate the stress again, because our force is reduced. So now it's only 30,000 pounds force divided by the same cross-sectional area, which was 0.78540 inches squared. And now I'm going to redo that calculation, but with 30,000 divided by 0.78540 gives me 38,197 psi. 38,197. I lost my marker. Oh, there it is. 38,197 psi. Now, once again, pause right here and compare this against the yield stress. The stress in this problem, when I apply this force, is 38,197 psi. The yield stress was 50,000 psi. So we're less than the yield stress. That means the elastic modulus still applies. So we're good. We can proceed. All right. So remember, the process we're going to use in this problem, we're going to calculate the stress. That's step one. Step two is we're going to use the definition of the elastic modulus to get us strain, because the elastic modulus is equal to the stress divided by the strain. Now we know the stress and we know the elastic modulus, so we can find the strain. That's step two. In step three, what we're going to do is we know the strain, we know the original length, so we can find the change in length, which is the stretch. All right, so that's where we're going. So in step two, we use the definition of the elastic modulus, which is equal to rise over run, stress divided by strain. And in this case, what are we trying to find? We're trying to find the strain. We know the stress, it's that, and we know the elastic modulus, it's that. So rearrange this to solve for the strain. So multiply both sides times the strain. then divide both sides by the elastic modulus. And what you'll get is the elastic modulus, excuse me, the strain is equal to the stress divided by the elastic modulus, right? Just a little bit of algebra there. I want to get the strain all by itself on one side. So I multiply both sides times the strain. That gives me elastic modulus times the strain equals stress. And then I want to get strain by itself, so I divide both sides by the elastic modulus, and that gives me the strain is equal to the stress divided by the elastic modulus. All right, so we know these two. Plug in for the stress, and you get 38,197 psi. We know the elastic modulus is 500,000 psi, and now we plug these in. 38,197 divided by 500,000, and my strain is 0.07639 inches per inch, because that's the units for strain. So it's 0.07639. Again, that's a few more sig figs than I would normally use, but I'll round it after I finish with the problem. Okay, that's our strain value. That's step 2. And the last step in this problem is to say, well, the strain, which is that, the strain is equal to the change in length or stretch divided by the original length. And in this case, what I want to find is the change in length. How do I get that by itself? Well, I multiply both sides times the original length. So rearranging this equation for the change in length gives me change in length equals the strain times the original length. Okay, so plug in numbers there, and the strain is from here 0.07639 inches per inch, and the original length was 4 inches. So these inches cancel out, and I'm left with just inches in the numerator. So take 0.07639 times 4, and you get 0. Now I can round a little bit, so I'll round to 3 sig figs here. 0.306 inches. So the change in length is equal to 0.306 inches. Okay, that's it. That's the answer to our problem. So make sure that you pause after you calculate the stress for the first time in any calculation problem and compare it against the yield stress. So remember in when we were talking about this a couple of weeks ago, I said there's kind of 2 ways I can ask you this problem. I can tell you what the force is and ask you what's the stretch. Or the opposite type of problem is I tell you it's allowed to stretch by a certain amount. How much force can I apply? So let's do a similar problem like that. Let's do one of those types of problems. So let's use the same specimen, all right? Same specimen, same material properties, just to make things a little bit easier. But let's say we're using the same specimen as before. So this is problem number 2. Same specimen as before. And we're going to say how much force would cause the specimen to stretch or extend by 0.18 inches. All right, so we got the same exact specimen made out of the same material as before, and we want to know how much force can I apply before the specimen stretches by 0.18 inches. So this is like the allowable stretch. What is going to be the force that causes that allowable stretch? All right. So what we want to calculate is the force, right? We want this force, and we can calculate the force once we know the stress and the cross-sectional area. I know the cross-sectional area, it's the same as before, but I don't know stress. So I could write the equation for stress, but there'd be two unknown variables. So that doesn't do me any good yet. But can I get the stress? Yes, I can get the stress if I know the elastic modulus and the strain. I know the elastic modulus, that's a material property, and it was given before, but I don't know the strain. All right, and can I get the strain? Well, I can get the strain if I know the original length of the specimen and the change in length of the specimen. Can I get that? Yes, I can, because that's the change in length, and I know the original length, it was 4 inches, remember? So that's our method for this problem. It's going to be pretty much the exact opposite as the previous problem. We're going to calculate the strain. We're going to use that to get the stress. We're going to use the stress to get the force. Okay, so step 1 is going to be to calculate the strain in this problem. The strain is the change in length divided by the original length. Change in length is 0.18 inches, and the original length was 4 inches, right, from the previous problem. Okay, so I can calculate the strain. 0.18 divided by 4 gives me 0.045 inches per inch. 0.045 inches per inch. Okay, that's step 1. Now that I know the strain, I can use the definition of the elastic modulus by saying that the elastic modulus is the stress divided by the strain, rise over run. And I can use that definition to solve for the stress, because now I know that, it's that, and I always knew this, it was given, it's the material property. So I can rearrange this equation to solve for the stress. And I'm going to do that by multiplying both sides of this equation times the strain. So I'm going to get stress is equal to the elastic modulus times the strain. All right. So those might look like two E's, but they're not. That's the capital E for elastic modulus, and that's the Greek letter epsilon for strain. Okay, and the elastic modulus was 500,000 psi. That was given before in the first problem. It's a material property. And the strain, we just calculated, it was 0.045 inches per inch. All right, so I plug those into my calculator. 500,000 times 0.045, and I get 22,500. It's going to be PSI. So the stress equals 22,500 PSI. And now, last step in this problem, I can use my definition of the stress. Stress equals force divided by area. And I can use what I know, which is the stress, as well as the cross-sectional area, and I can find the force. All right, so I want to find the force, so I rearrange this equation by multiplying both sides times the area. Force equals stress times the area. The stress we just calculated, it's 22,500. I'm going to write it like this: pounds force per inch squared. That's PSI, pounds per inch squared. And the cross-sectional area, it's the same specimen as before. And from before, we knew the cross-sectional area was 0.78540 inches squared. 0.78540 inches squared. Inches squared cancels out. And my force is 22,500 PSI times 0.78540. That gives me 17,672, round to 672. 17,672 pounds force. So that is the amount of force necessary to cause this specimen to stretch by 0.18 inches. All right. Oh, you know what? I did kind of overlook something. My mistake. I should have at this point, I should have compared this stress. Compare to the yield stress. So we need to compare that. In this case, I guess we kind of lucked out because the stress in this problem is less than the yield stress. All right, so we know we can proceed, but you should check right there. The first time you calculate stress in the problem, you should compare it against the yield stress. As long as your stress is less than the yield stress, go ahead, you can proceed, you can solve the problem. If it exceeds it, then you can't, you have to stop. All right, so I think that is a pretty good review problem for right now. You do want to make sure that you are very comfortable doing calculation problems like that, because there is a very good chance that on the exam you will see a couple of calculation problems kind of similar to that. So make sure you are comfortable doing those, along with the problems in the lab manual. That's also a very good review worksheet. All right, so I'm going to switch over and share my screen to go over some of the topics that we've talked about in the last month or so of the class. All right, this is a review for exam 2. The format of the exam is going to be pretty similar to the way exam 1 was. The exception is that there's going to be a few more calculation problems in exam 2 because we've done more calculation in this second third of the class. All right, so you can definitely expect some calculation problems on tensile and or compression testing. But there will still be a lot of multiple choice questions. I think it's fair to say that the majority of the exam will be multiple choice questions. There's also going to be true false questions, and like I said, some calculation problems where you have to do the calculation on a piece of scratch paper with a calculator, and then type in the correct answer into ReggieNet. Make sure that when you sit down to take the exam, make sure you have a writing utensil and a scratch paper and a calculator so that you can do those calculation problems. Probably also you want to have your lab manual. You want to have any notes that you took while watching the videos. Textbook. Like I've said before, you can use anything you want on this exam with the exception of another person in the class. So here's a quick review of the material science portion that we talked about in the first couple of weeks of the class. We talked about 5 different groups of engineering materials and their pros and cons, advantages and disadvantages. We talked about 4 different types of bonding, 3 at the atomic level, 1 at the molecular level. We talked about what determines the phases of matter, whether a certain material is going to be a solid, liquid, or gas, and what affects the boiling and the melting temperatures of those materials. The 3 different atomic level bonding mechanisms that we talked about were ionic bonds, covalent bonds, and metallic bonds. So you should know some details about each one of those different types of bonds and the characteristics that they give to the materials that they are a part of. And then the molecular level bond we call intermolecular bond. Another word for that is van der Waals forces, which create the intermolecular bonds. And you should know that a specific particularly strong type of intermolecular bond is a hydrogen bond. And you should know what types of elements typically form hydrogen bonds. Then we talked about lattice structures. That's part of material science. So you should know something about lattice structures and how many different types of lattice structures there are. The 4 main ones that we talked about that are most prevalent in materials are simple cubic, body-centered cubic, face-centered cubic, and hexagonal close-packed. You should know some mechanical properties and characteristics of each type, and you should know the packing factor for each type as well. Then we talked about alloys, that is other materials that you add in to a base material to create a mixture. And we talked about interstitial alloys as well as substitutional alloys. You should know what that means and maybe a few examples of each. We also talked about grains, especially in the context of metals. They're particularly relevant to metals. We talked about how they form and the influence that the grain size has on the mechanical properties like strength and ductility and hardness. And briefly in that first section of the course, we talked a little bit about metals, a little bit about ferrous and non-ferrous metals, but then we talked more about it in this second third of the class. And we talked about some general properties of ferrous as well as non-ferrous metals. Then we took exam 1, and then we move into the new material for exam 2. So we talked about tensile testing and how we do tensile testing. What is the independent variable? What is the dependent variable? We've talked quite a bit about stress calculations and how to calculate stress and how to calculate strain. And we've talked about necking, and you've seen necking in several of the labs. Lab 4 and Lab 5, you definitely observed necking in several of the different materials that we tested. And some more definitions and nomenclature that you should be familiar with. You should know what stress and strain are and how to calculate them. Same with elastic modulus. You should be able to look at a plot and identify where is the yield strength. Also, what does it mean? What is the yield strength? Same thing with the ultimate tensile strength. Same thing with the failure strength. And you should know these terms. Ductility, what is ductility? What does it mean? As well as brittleness. If something is brittle, what does that mean? And how would you know if it was brittle? By looking at a stress strain curve. You should be able to look at a stress strain curve and tell me if a material is relatively ductile, comparing material A and material B on, say, 2 stress strain curves. You should be able to tell me which one is more ductile. You should be able to tell me which one is more brittle. And you should be able to eyeball it and tell me which one is tougher by knowing the definition of tensile toughness. With regards to tensile testing, stress calculations, we talked about the difference between true stress and engineering stress. And we talked about how we pretty much always use engineering stress. That's far more common. But you could calculate true stress, and I would expect that if I gave you the data, you could use the changing cross-sectional area as it's changing during a tensile test. You certainly have the ability to do that. It's just a pain in the butt usually, so we don't usually do that. And then for strain calculations, we talked about 3 different legal, allowable ways per the ASTM to do strain calculations. And we actually did 2 of them. We did the 2 best ones in our class, because remember in Lab 4 and part of Lab 5, we used the moving crosshead, which gave us extension data. And then for the other part of Lab 5, for generally the elastic region, and sometimes a little bit of the plastic region, for the metals, we used the extensometer, right? So those are 2 of the 3. Those are the best 2 of the 3 different ways to calculate strain. You should know all 3 of them. I already said necking. I don't know why it's in there twice, but yeah, you should know what necking is. Toe compensation, you should be able to identify that on the curve and know what it's caused by. Generally, what it's caused by is slack in the fixture that you have to pull out. You have to pull out the slack before you can really exert a force. Think of like, I don't know, right now I'm thinking of like a tow truck pulling out a car in a ditch, right? And before the tow truck can really pull out the car in the ditch, it's got to pull the slack out of the tow line, right? It's not really going to exert any force on the car to pull it out of the ditch until all the slack is taken out of the tow line. So that's basically what toe compensation is. You're pulling the slack out of the test fixture. And sometimes it's kind of unavoidable that there's just some slack in those grips, in the attachment between the grips and the moving crosshead or the stationary part of the instron. You get the idea. Work hardening, you should know what that means, as well as which region on the stress strain curve you get work hardening in. So where in the stress strain curve does work hardening occur? If I gave you a stress strain curve, you should be able to pick out different regions on the stress strain curve. For example, what region does elastic deformation happen in? What region does plastic deformation happen in? What region does work hardening happen in? And what region does necking happen in? Some calculations. Like I said before, you should be able to calculate stress and strain. Given a stress strain curve or data, either one, you should be able to calculate the Young's modulus. Remember, it's just the slope. It's the rise over run, stress, change in stress divided by change in strain. And like we just did in the calculation problems, that's exactly what these two are right here. So if you know or can calculate from data or from the plot, if you can get the Young's modulus, and if you know the dimensions of the part and the force, then you can calculate the stress and the strain. And you should also be able to, okay, these are the two that I was talking about before. These are the two that are similar to the calculations that we just did in the first part of this video. You should be able to calculate the change in length or the stretch, extension, they all mean the same thing. The stretch from knowing the strain and the gauge length, and you should be able to calculate the force that would produce a given strain or a given change in length of the specimen. The only equations we've really used in this section are these equations right here, and they apply to tensile testing or compressive testing, either one. All right, so here's our definition for stress, here's our definition for the elastic modulus, and here's our definition for strain. I don't know why that got cut off on the bottom, but that says original. That's the original gauge length of the specimen. We had a day where we talked about ferrous metals, so you should know the steps in the steel production method. You should know about blast furnaces. What are the inputs? What are the outputs? What does it do? You should know the 3 different types of steel furnaces, which remember are different than blast furnaces. You should know the pros and cons of each of those 3 different types of steel furnaces. And you should know a little bit about the forming of the specimens that happens after it comes out of the steel furnace, like rolling, forging, and drawing. We talked about identifying steel by its identification numbers. For example, 1018 or 1040, 1045 steel. Those are the ones, I think 1045 and 1018, that's what we did in some of the recent labs. But I could tell you, any steel, like 1010 or 1090 or 1082 steel. Some of those aren't very common, but same principles apply. You should be able to tell me what are the alloying elements, and you should be able to tell me how much carbon is in those steels. And then that leads to, well, what's the difference mechanically between, say, 1015 and 1085 steel? What's going to be the difference between those steels in terms of its strength, its price, ductility, hardness, and heat treatment processes? That last part I didn't emphasize. I think I mentioned it, but I didn't emphasize it. But generally, the more carbon you have, the greater its ability to be heat treated. All right. We'll talk about this after the exam, but this is actually one of the first sections in the last third of the class is heat treatment. And heat treatment basically has to do with the form that the carbon takes inside of the steel structure. So if you have more carbon, you have a greater ability to do heat treatment processes. If you don't have very much carbon in there, well, there's not much you can do with heat treatment. We talked briefly about tool steel. Why would you use it, and what are some differences from regular old plain old steel? And same thing with stainless steel. We talked a little bit about its special properties. What does it do? How does it behave differently? It's not enough just to say that it doesn't rust. You know, that's not enough detail. But what gives it its special properties, and how is it different from normal plain old steel? We spent a little bit of time talking about cast iron and 4 different types of cast iron, as well as the casting process briefly, and why you would want to use a cast part. What types of parts are good for cast materials or cast iron. And the 4 different types we talked about were gray cast iron, white cast iron, malleable cast iron, and ductile cast iron, or DI. You should know the properties of each type and why they have those properties. Especially, definitely pay attention to the differences in how the carbon is arranged, the formation of the carbon in each one of those 4 different types of cast iron. Then we spent a day talking about non-ferrous metals, and we spent the most time in this lecture talking about aluminum. So probably you could expect more questions on aluminum than the others. Make sure you are familiar with the production method called the Hall method, which is kind of like the electric arc furnace for steel, but it's a little bit different. The inputs and outputs are a little bit different for the Hall method of aluminum production. You should know what anodizing does. Remember, it's kind of similar to stainless steel. And you should know the identification codes. Remember those 4-digit numbers for aluminum. And they're very different from steel, so make sure you look at both of those. You should know what the different numbers for steel identification mean, and also what they mean for aluminum. They're totally different between the two, so don't get them confused. Then we talked in just a little bit of detail about 5 other non-ferrous metals that I'd say are probably some of the more important non-ferrous metals, like copper and brass and lead and magnesium and zinc. And what are some important properties, pros and cons of each one of those? And the last thing we talked about in this section of the course was compression testing. We said it's very similar to tensile testing. It's just the opposite. You're just squishing it this way instead of pulling it apart this way, but the same effects apply. You still calculate stress the same way, and you still calculate strain basically the same way as well. One way that it was different is the failure mode, and there are mainly 2 different types of failure modes for specimens under compression testing. Generally, they're either going to fail by barreling or by shear fracture. And you should have an idea of what types of materials fail under each different failure mode. You should be able to calculate the modulus, which we now call the compressive modulus, or the modulus in compression, which is very much like the elastic modulus, which we used for tensile testing. It's just now we're calculating the slope of that line, still stressed over strain, but now it's the slope of that line for a compression test. We've still got elastic deformation, we still got plastic deformation in compression testing, and we still have a yield stress, so make sure you can identify that. The labs that we've done in this third of the class, Lab 4 was tensile testing of plastics, and you practiced calculating stress and strain and plotting them and labeling the important points on those plots, calculating the elastic modulus, the elongation, and then generally comparing and contrasting the materials, which ones were the strongest, which one had the highest ultimate tensile strength, which one had the highest yield stress, and so on. Lab 5 was very similar, but we did woods and metals. And with the metals, we used an extensometer. So remember that, remember how we used the extensometer to calculate the strain. But when you're looking at the data, it didn't look any different, right? You couldn't really even tell what the source of the extension data was, whether it was the extensometer or whether it was the moving crosshead. But remember, we said the extensometer is actually more accurate when the load for the testing is approaching the limit of the testing device. And in this case, it was, especially those steel specimens, was getting close to the limit of what our test machine can handle. So when it gets close to that, what can happen is the moving crosshead can actually bend slightly. You're not really going to notice it, but it can bend, and that will affect your data, and that will affect your calculation of the elastic modulus. All right, so same types of things that you calculated for lab 5 as compared to lab 4. And then lab 6 was very similar, but it was kind of just the opposite, where we were squishing all those specimens instead of pulling them apart in tension. That wraps up the review for exam 2. I'm going to set up the exam kind of similar to the way I set up exam 1, where it's going to be available anytime on Thursday. You just have to pick a 3-hour window to do it. So the time limit is going to be 3 hours, but you can pick what time you want to take it. It's going to open at 12 o'clock a.m., midnight, on Thursday, and it will remain open until 11:55 p.m. that night. So allow yourself plenty of time. Don't start the exam at 11 p.m. Make sure you start before 9 p.m. so that you get the benefit of that full 3 hours. Otherwise, it's silly to cut yourself off, because RegNet will submit whatever you have done at 11:55 p.m. So give yourself plenty of time. I'll probably make it somewhere around like 50 to 60 questions. I don't know. I haven't actually set it up yet, so I haven't decided how many questions. And it kind of depends on what type of question I ask too. If I have more calculation questions, then I'll probably have fewer questions overall. But there'll be a mix. There'll definitely be a mix between conceptual, multiple choice, true-false questions and calculation questions where you have to enter a number as your answer. There will be more calculation questions on exam 2 than there were on exam 1, just because we've done more calculations in the second third of the class than we did in the first third of the class. So that's why I said to make sure that you are comfortable with those review calculation worksheets that we've done in this section of the class. So that's about it. Let me know if you have any questions, and I wish you the best of luck on the exam. I hope everyone does great on the exam, and I'll see you next time.